Hey everyone, it's Justin again. In the last lesson, we mentioned that asymptotes don't always have to be vertical or horizontal. In this video, you'll see why. By the end of this lesson, you should be able to find oblique asymptotes from the equation of a rational function. First, we'll define what exactly an oblique asymptote is, and then we'll explore when and why these asymptotes happen. Then, we'll practice with an example problem. To this point, we've only seen vertical or horizontal asymptotes. The function 1 over x has both, as do many other rational functions. But this function has an asymptote that's slanted. The official name for this sort of asymptote is an oblique asymptote. You may also see it called a slant asymptote. The word oblique actually just means slanting. This oblique asymptote serves a similar role to the horizontal asymptote in 1 over x. In both cases, as the function goes off to the left and right, it's getting closer and closer to that dashed line. An important note is that functions can cross their oblique asymptotes, just like how they can cross horizontal ones. Now, why do some functions have oblique asymptotes? And how do we find the equations of these asymptotes? To answer both of these questions, let's look at an example. Notice here that the numerator has a higher degree than the denominator. That means it doesn't have a horizontal asymptote, like we learned from the last lesson. When we look at the graph, we confirm that there is no horizontal asymptote, but there might be an oblique one. In a previous lesson, we used polynomial long division to simplify expressions like this. Why not try it here and see if the result can tell us anything new about the function? Here are the steps for polynomial long division again. Pause the video now and see if you can simplify this function. Since we did the review pretty recently, we're not going to go over this in quite as much detail, but we will show you the work so you can compare it with yours. Now, does your answer match what's shown here? If you need another refresher, you can always pop back over to the polynomial long division review to resharpen your skills. This is the simplified version of the function. And the slant asymptote is hiding in plain sight in this new equation. Let's check out the graph to see why. You might have noticed that the graph is counting by tens here. We're going to zoom in on part of the graph near the origin. Now that we're zoomed in, here's a cool and helpful fact. For functions like this, the equation of the oblique asymptote will be the result of the long division, excluding the remainder. In this example, that was 2x minus 6. So let's put the line y equals 2x minus 6 on this graph to check it out. It would have a y-intercept at -6 and a slope of 2. This certainly looks like it could be the asymptote. If we put this line on the original zoomed out graph, it's clear that this is the correct asymptote. So why is the line y equals 2x minus 6 the asymptote here? Why does the function get closer and closer to this line as you go further left or right? Well, think about what we mean when we say going further left or right. That means moving in the direction of the x-axis. Going further to the right, for example, means going higher and higher values of x, like to x equals 100 or 1,000 or 1 million. And at this point, it's actually better to look at the other part of the function, the remainder over the original denominator, 13 over x plus 3. What happens to this part of the function when x is 100 or 1,000 or 1 million? As x increases, the fractional part would get smaller since x is in the denominator here. 13 over 1 million plus 3 would be a really, really small number. And it would keep getting smaller as we go further to the right onto bigger and bigger values of x. But the 2x minus 6 will also keep getting bigger and bigger. This table shows what happens as we move to the right, meaning as we increase the value of x. Eventually, the 13 over x plus 3 would be such a small number that it would hardly affect the 2x minus 6 part at all. That's why the function gets closer and closer to the line 2x minus 6. When x is enormous, it's basically 2x minus 6 plus a number so small that it almost doesn't matter. But this part, no matter how small, would never go all the way down to 0. The function would still be 2x minus 6 plus a teeny tiny number. That's why it's an asymptote that the function never quite reaches. A similar situation happens when we make x more and more negative, which is why it's an asymptote in the negative direction on the graph as well. Take a moment to think through it and convince yourself. It might be helpful to create a table like this in your notes for negative values of x. Pause the video now and unpause when you're ready to move on. All right, now let's look back at the division that we did for this problem. Now that we're familiar with how oblique asymptotes work, there's a helpful shortcut we can use when doing these calculations. Here's the work we did before. The oblique asymptote was just this part of our answer to the polynomial long division. So if you're only looking for the oblique asymptote, you only need what goes above the division symbol. There's no need to calculate the remainder since we've just seen that the remainder doesn't affect the asymptote. That means once you have the division done up to this step, you have the oblique asymptote. In calculating these asymptotes, the challenge is just making sure you're careful with your polynomial long division. Now that we understand how oblique asymptotes work, we can add them to our list of asymptote cases from the previous lesson. These oblique asymptotes happened when the degree of the numerator was greater than the degree of the denominator. So we need to expand on case 3. But a function actually will not always have an oblique asymptote in case 3. It only happens when the numerator is exactly 1 degree higher than the denominator. Otherwise, the long division won't give us the equation of a line. It would get a lot messier. So, if the degree of the numerator is 2 or more higher, there is no linear asymptote. This second part of case 3 is something we don't really get into in this course since it can get pretty complicated. But it's also pretty cool. So if you're curious, you should definitely explore it more on your own. In any case, recalibrate your brain with this new case 3 as we move on to an example. Find the oblique asymptote of this function. Try to solve this problem on your own. Pause the video and unpause it when you think you have an answer. Like the problem we talked about during the lesson, we won't show every individual step of the division. If you aren't feeling confident in your polynomial long division, take a quick break to look at the review lesson on this topic. This example here is the same as the final example in that video. All right, is this what you got up to this step? Remember, you can stop once you're here. All we need is that x minus 3 because the rest would be part of the remainder. The equation of the oblique asymptote is y equals x minus 3. We've now learned about a few different properties of rational functions. They can have holes, vertical asymptotes, horizontal asymptotes, and now oblique asymptotes. Knowing how all of these work, how to find them, and how to graph them is super helpful when you're trying to make a sketch of a given rational function. We'll be trying that out in the next few lessons. See you then! Hey.